In this video, we are going to learn how to track an object across video frames. Specifically, we will talk about object tracking using a histogram-based tracker, tracking occluded or hidden objects using Kalman Filter, and finally some tips to track multiple objects. We will use the example of tracking a moving ball. Tracking an object constitutes estimating the trajectory, change in location and state of an object over time, including change in size or color. For example, let's switch to MATLAB. Let's right-click on the file balltracking.m and then run it. Here, we search for the object in all the frames of the video. In some situations, such as high frame rate applications or where the object detection is a computationally expensive algorithm, this is inefficient. As an alternative approach, we will detect the object in the first image and then search for the corresponding location in the subsequent images. Thereby, the assumption is that the object does not move substantially between two subsequent frames of a video. We will first use a histogram-based tracker for our ball example. In some of the video frames, the ball will run through an occlusion and thus we cannot track it in these frames. We will then use a Kalman filter for predicting the position of the ball during this time. Let's go back to the presentation. The histogram-based tracker uses a continuously adaptive mean shift algorithm for object tracking. The tracked object is identified by the histogram of object pixel values based on color or intensity. There are three steps to do this. First, we create the tracker object. Then, we initialize the tracker with the initial region of interest. Then, we loop the tracking algorithm over the frames in a video to track the object of interest. Let's switch to MATLAB to see how we can do this. Let's open the starter script histogram tracking_start. In the script, we have already been provided with comments and initial code that will help us develop the algorithm. We see the video file reader system object set up to read the file ball.mp4. We see this file here. Right-click on this file and open it outside MATLAB. This is the video we will be analyzing to track the ball. Let's go back to the script. We also see the deployable video player that will help us visualize the result. Now, let's set up the histogram-based tracking using the system object vision.histogram-based-tracker. This is the first step. Next, we need to initialize the tracker with the initial position of the object of interest. This position is a 1/4 matrix consisting of x, y, width, and height bounding box coordinates. X and y represents the lower left corner of the bounding box. We can use an object detection algorithm such as blob analysis to retrieve this information. For demonstration purposes, let's manually select the region of interest in the object. To do this, let's retrieve the first frame from our video using step and display it using the imshow command. Then we will use the imrect command to get the region of interest. We can then use the provided utility function getLog and feed in the imrect object to get the bounding box position in the required format. Let's run the code. A figure pops up for us to select the region of interest. Let's select the yellow ball and double-click inside the region of interest. Now if you go back to the command line, we see the returned position of the selected region, where the 4 elements corresponds to x, y, width, and height. Next, let's initialize the tracker using the selected region of interest. Initialization is done using the initializeObject function. Let's go back to the script. This function takes in the tracker object as input, the input image, and the region of interest in that image. The input image must be 2D, thus we cannot pass an RGB image directly, which is a 3-dimensional array. The selection of an appropriate representation of the input image is important for a good tracking result. For our example, let's use a simple 2D representation of the image first, that is, the red channel of the image, and analyze our results. Finally, let's pass the region of interest obtained through the imrect command as the third argument. Another parameter we can specify during initialization is the number of histogram bins, which affects the ability to track the object in the presence of changes in visual characteristics such as lighting changes. For our example, we will leave this at the default value of 16. Now, to apply the tracking on our subsequent video frames, let's use a while loop as before. Inside the loop, we will read in the video frame. Then, to track the object, we will use step on the histogram-based tracker object with the red channel of the current frame or image as an argument. In addition to the bounding box, the algorithm also outputs two other parameters, namely the orientation and the confidence score. Please refer to the documentation link in the resources section to get more information about this. We can now visualize the result of the tracking by inserting a rectangle onto our original frame with the output of step and display it on the video player. We will also include an additional pause in the loop for visualization and demonstration purposes. Let's run the code. Select the region of interest such that it covers not only the ball, but also some region outside of it, for example, a bit of the hand part of the image, and then double-click inside the selected area. It starts to track the ball. However, the tracking diverges as we move to subsequent frames. This is because our initialization image did not include only the ball, but also some part outside the region of interest. This meant that once the ball moved away from the hand, the histogram of pixel values couldn't converge to track the ball. Let's go back to the script. Let's rerun the code. This time, let's make sure the region of interest contains only the pixels that corresponds to the region of interest, that is the yellow ball, and double-click inside the selected area. Now we can see that the tracking of the ball is better. However, the tracking gets lost once the ball disappears behind the occlusion. Let's analyze this result by further plotting the confidence score of the tracking. Let's go back to the script. We will initialize an index variable and use it with the score variable. Let's increment the index variable inside the loop. And then outside the loop, let's plot the score array against its indices. Let's rerun the code. Select the area of interest and double-click inside the selected area. We see from the confidence score plot that despite the fact that the tracking was lost, the confidence scores are still relatively high. This means that the red channel we chose for tracking was not the best at discriminating the yellow ball. Once the white paper occludes the ball, the tracking mistakes the paper for the ball. Let's go back to the script. Now let's change the supplied input image so that the tracking operates on the YCBCR color space instead of the RGB color space. To do this, first let's convert the input image from RGB to YCBCR before the initialization, and then use the CB plane for tracking. Note that based on the application, it can be one of several different things. For example, the hue channel of the HSV color space, an intensity or gradient image, or a texture filtered image. Similarly, let's also change this approach within the loop. Let's rerun the code. Select the region of interest and double-click inside the selected area. We see that the tracking is not distracted by the white paper occlusion anymore. From the confidence score, we see that it diminishes as soon as the tracking is lost. This is a better input image to use to track our yellow shaded ball. One way to find an appropriate feature map for a color image is to use the color thresholder app. We have already talked about this in a previous video such as the blob analysis, so please refer to that for more information. Another thing to note in this result was that the tracking fails even after the ball reappears. This is a characteristic of the histogram-based tracker as it does not handle occlusion automatically. To solve this, once the object is lost, the search window needs to be reinitialized when the object reappears. We can use the confidence score as a metric to do this. Let's go back to our script. We will track the object every iteration as we did before. Now we have the score for the current frame. We can say if score is greater than 0.5, output the tracking result as we did before. Else, we were unable to successfully track the object. So we will need to find it again using our object detection algorithm. Next, there is no guarantee that we will be able to find the ball. This is because in case of an occlusion like the white paper, we won't find the ball until several frames after. So if the ball is found, we can reinitialize and track again. Otherwise, ball was not found, so we just output the original video frame unaltered. Now that we have the logic for our algorithm built, let's fill in the MATLAB code to do this. Outputting our tracking result is exactly the same as this code here. So let's just cut this code and then paste it here. Next, to find the ball, we will use the provided utility function segmentBall. This takes in the image and pixel area as inputs and gives the bounding box and center position as the output. Bounding box is the first output, so we will request only that from the segmentBall function. So, if the detected location is not empty, we can reinitialize using the initialize search window function. This function takes in the tracker object and the detected location as input. Then once we have done this, we can use this information to track the object starting from the current frame. Else, we just output the current frame. Let's run this code. Select the region of interest and double-click inside the selected area. Now we see that once the ball is lost behind the occlusion, the tracking is lost. However, we are able to retrack once the object comes into the view again. From the confidence score plot, we see that the score is low in the middle part when the ball is lost, and then relatively high again for when it is available in the frame. Let's go back to the presentation. We talked about the histogram-based tracker. We use the histogram-based tracker system object. We then initialize the tracker using the object, a 2D representation of the image where the object can be tracked appropriately, and a region of interest. We use the initialize object function for this. We then used step on our tracker object with our current video frame as an argument to perform tracking. Here, if the confidence score was high, we continued tracking. For low confidence scores, we tried to reinitialize tracking using the initialize search window function. When implementing tracking applications, there are several issues that may arise, such as object is hidden behind an obstacle, object is visible but due to noise or lighting issues, segmentation fails, large search space for tracking the object. When tracking multiple objects, the object's paths may cross each other. All these will prevent us from obtaining the complete trajectory of the object. We can overcome this by predicting the next position of the object whenever tracking fails. Especially for large images and complex detection algorithms, this can save computational time. One common method for predicting an object's future position is the Kalman filter. The Kalman filter has two important steps. The first is prediction. Based on an ideal motion model and information about previous states, it predicts the current states. The motion model could be either a constant velocity or a constant acceleration model. In reality, however, motion is rarely constant velocity or acceleration, leading to inaccurate predictions due to the ideal motion model assumption. We will see in a bit how to address this ideal situation. The second step is correction. Based on measurement or observation, the Kalman filter can correct itself. This measurement could be any object detection algorithm that could return the center of the detected object. Note here that we are talking about the center of the detected object and not the bounding box around the detected object, which was the case in the histogram-based tracker. We will use the configure Kalman filter function to create the Kalman filter object and configure its properties. We can set 5 properties using this function. 2 of these are associated with the prediction step, namely motion model and motion noise. 1 is associated with the observation step, namely the measurement noise. And finally, 2 properties are associated with the initial state of the object, namely its initial location and the initial estimate error. Let's switch to MATLAB to see what these properties mean and how we can configure them to use the Kalman filter. Let's open the starter script Kalman ball tracking _start. In this script, we have been provided with comments and initial code that will help us develop the algorithm. We see the video file reader system object set up to read the file ball.mp4. We also have the deployable video player that will help us visualize the result. First, we need to initialize the position of the object. To do this, we need the center position of the object in the first frame. Recall that we used a 1/4 position matrix for the histogram-based tracking example. In the Kalman filters case, we need the center of the detected object. Similar to the previous example, we will manually select the region using the imrect command. Then we can get the center position of the object of interest using the provided utility function getLock again. This time, we want the center location of the object of interest, so we will request the second output of the getLock function. Let's run this code. In the figure window that pops up, let's select the area of interest and double-click inside the selected area. Let's go back to the command line. So here we see the XY center location of the box that we selected. Let's go back to the script. Next, let's set up the properties of the Kalman filter. Recall that there were 5 parameters. First, let's set the motion model. We can select either constant velocity or constant acceleration motion model. For our example, let's set it to constant velocity motion model. This is the ideal motion model assumption for our tracked object. Shortly, we will talk about other parameters that will help us model the real motion behavior. Next, we set the initial location of the object. This is from what we selected using the imrect for our example. The third parameter is the initial estimate error. This sets the expected variance between the actual initial position and velocity and the set initial position and velocity. For example, a position variance of 9 means there is a position standard deviation of 3 pixels around the actual location. The first element corresponds to the position and the second velocity. If we set the motion model to constant acceleration, we will need to provide 3 elements where the third corresponds to an acceleration variance. Let's set this to a 1/2 vector 10, 10. The last 2 parameters help us model the real motion behavior. Motion noise tells us how far away from the assumed constant velocity or acceleration model is our real motion. This is a 2 or a 3 element vector depending on the motion model, like the initial estimate error. Let's set this to a 1/2 vector 20, 20. Finally, the measurement noise parameter is a measure of how accurate we think our detection algorithm is. Let's set this to a value of 200. We will see the effect of these noise parameters later in this video. Now let's feed these parameters into the configure Kalman filter function that will return us a Kalman filter object. Next, let's apply the Kalman filter. Let's begin a loop to apply these for consecutive frames. We will first read in the frame. For every frame, let's predict the tracking location using the Kalman filter with the predict function. We can then visualize the result using the insert shape function. We will visualize the tracked location with a green circle and a specified radius. This is the first step, the prediction step. Next, for the correction step, we first try to detect the ball. If we detect the ball, we can use the detected location to correct or update the Kalman filter. To detect the ball, we will use the provided segment ball function. Recall that we need the center of the detected location. So in this case, we will use the second output of the segment ball function. Then, if the detected location is not empty, or in other words, if we actually detect the ball, we can update the Kalman filter using the correct function and the detected location. To visualize the result, let's mark the video frame with a blue circle and a smaller radius to show the detected location. Finally, let's visualize this frame using a video player. We will also use an additional pause in the loop for visualization and demonstration purposes. Let's run this code. Select the area of interest. Double-click inside the selected area. Here we see the tracked location with the green circle and the detected location using the blue circle. We can see that initially the tracking takes some time to converge to the detected location. The tracker remains active even in the presence of an occlusion, and then corrects or updates itself when the ball reappears. Now, let's change the motion noise and measurement noise parameters to see the effect it has on tracking. Let's go back to the script. First, let's increase the motion noise from 20 to 200. This means that we are assuming that the motion model that we have selected is not a good representation of the actual motion. So the tracking will depend more on the detection algorithm instead of the motion model. Let's run the code. Select the area of interest and double-click inside the selected area. Here we see that even in initial stages, the tracking is very close to the detected position. After the ball reappears from the occlusion, we see that the tracker immediately shifts focus to the first detection. Let's go back to the script. Let's reset the motion noise value to the previous value and increase the measurement noise value from 200 to a 2000. This means we are assuming our detection algorithm is not that accurate and rely more on the assumption of the motion model to track the object. Let's rerun the code. Select the region of interest. Double-click inside the selected area. We see that for a good bit in the initial stretch, this is not a good assumption in our case. The tracking fails to converge. This is because the measurement noise is high, so the tracking is going to follow the motion model more than the measured or the detected location. In this way, based on our unique applications, these values affect the long-term performance of tracking. Let's go back to the presentation and do a small recap. We just talked about how to set up the Kalman filter using the configure Kalman filter function. We discussed the various parameters associated with it. Next, we use the predict and correct function. The predict function is used to estimate the position based on an assumed motion model, and the correct function is used to correct the predicted position based on measurement. We also talked about how motion noise and measurement noise affect the tracking behavior. The motion noise describes the difference between the object's actual motion and the motion model. Increasing this makes the tracking dependent on having an accurate object detection algorithm. The measurement noise describes the inaccuracy of the detected location. If we increase the value, the tracking may adhere closely to the motion model. Both parameters stay constant and thus may affect long-term performance. The next logical task is to think about tracking multiple objects at once. Let's switch to MATLAB. Right-click on Kalman multi-object.m and then run it. We see that the example tracks two balls crossing each other and maintains a unique identity to each of these detected objects. This is one of the challenges associated with multi-object tracking. In the example, the balls cross each other's path and maintain identity. What will happen if they collide and bounce the other direction? We can use Kalman filters to predict using motion model and measurements that we discussed before. Let's go back to the presentation to see some tips on how to do this. Suppose we have two detections in our current frame as shown here. Based on this, we would need to implement a track management system. Let's see the logic to do this. Suppose that our algorithm has already created 3 tracks. Each one of these tracks has a Kalman filter associated with it. We have 2 detections in the current frame and need to assign these 2 to either existing tracks or create new tracks. The first step is to calculate the cost for assigning a detection to a track. This can be done by using the distance function. The function calculates the distance between the detected and predicted position. A low distance means a low cost for assigning the detection to the track. The calculated costs are arranged in an m by n matrix. M corresponds to the number of tracks and n represents the number of detections. We will then supply the cost matrix to the assign detections to tracks function. The lower the cost, the more likely the detection gets assigned to a track. The input argument cost of non-assignment specifies the cost for not assigning a track or a detection. A higher cost of non-assignment means that it is very likely that the algorithm will assign all detections to existing tracks. This could lead to wrongly assigned tracks and detections. On the other hand, a low value of cost of non-assignment increases the chance of getting new objects. The last task the track management has to do is deleting tracks that were not assigned to a detection for several steps. If we did not detect the object for several frames, it is very likely that the object is not in the image anymore. We can store all the information related to one tracked object in a structure variable. Besides the Kalman filter itself, the structure contains a unique identifier for every track and the number of consecutive frames where the object was not detected in the image. This invisible count field can be used as a criterion to delete tracks. Please refer to the provided example and the relevant documentation link provided in the resources section to get more information about multi-object tracking. In summary, we talked about how to track objects. We first saw the histogram-based tracker. Then we talked about issues that arise when tracking and how prediction using Kalman filter helps with those issues. Finally, we saw the workflow and an example to do multi-object tracking. This concludes this video.